Obviously, to move further, we'll have to get into the details of how the winds grab hold of the ocean surface to drag it around and produce currents and transports. Wind has to grab the surface. It basically happens through friction, right? How far can we explain the distribution of the winds in the surface layer? Turns out that not in a great detail, but actually it doesn't matter. The bulk formula for wind stress, tau wind x and tau wind y, are given by the density of the air, a kind of a drag coefficient, wind speed at 10 meters, which is historical reasons of measurements from the ship deck. It's left at 10-meter winds, and wind speeds in the x and y directions. This is kind of what is known as the bulk formula for wind stress. So what does happen as it hits the ocean? There is a boundary layer within the atmosphere, but we are going to just worry about the wind stress that actually reaches the surface of the ocean. So there is the slab of the ocean. Think of the depth z and the sea surface at z plus delta z. So you have tau x at z plus delta z decaying to tau x at z. You can see that this arrow is longer than this arrow to give you a sense that as the winds try to drive the surface with friction, winds begin to die down deeper into the ocean, right? There is a friction layer, boundary layer, mixed layer, whatever we want to call it. And this is some depth over which the wind is being distributed. And looking at our equations of motion, we had written it as du dt plus 1 over rho ref. This is the big difference compared to the atmosphere. We can assume density to be constant, incompressible ocean in these particular terms. dp dx minus fv equals the friction. Obviously, we are heading to say friction is the wind stress, right? dv dt plus 1 over rho ref dp dy plus f times u equals friction in the y direction or the wind stress in the y direction. Writing this, assuming the low Rossby number regime, we drop the time terms and assume steady flow and just balance the Coriolis acceleration with the pressure gradient and the friction. So this would be just the Coriolis and the pressure gradient giving us geostrophy, except now we have winds which are giving us the frictional force. So look at this cartoon now, a little bit better than the first one we saw, where tau 0 is the wind stress at the surface. There is a Ekman layer delta. Why is it called Ekman layer? It turns out that Fridtjof Nansen had gone to the North Pole. He tried many times and succeeded in the end. He was a Nobel Prize winner for peace. Okay. Anyway, he asked his student. He asked a student, Walfried Ekman, who was working with Wilhelm Birknes. See how the historical names connect to each other. To figure out why ice was drifting at an angle to the direction of the winds. Apparently, Ekman sat down one evening and worked out the whole thing. His PhD was basically done in a few pages in one evening. Brilliant person, right? So here is the wind decaying to 0 at some depth delta. So z equals minus delta going from the surface. Tau is 0 at z equal to minus delta. So force per unit area in that case is just the wind stress force is just force per unit area divided by mass per unit area. So we're just taking a unit area of the ocean to do these calculations. So tau x at z plus delta z minus tau x at z divided by rho ref delta z. So unit area, rho ref times delta z will give us the mass. Delta z times unit area is the volume. Rho ref gives us mass. And that can be written, if delta z is small enough, 1 over rho ref d tau x dz. It's the gradient of the wind stress decaying into the boundary layer, in which case we can write the vector form of our frictional force as 1 over rho ref del tau del z. Simple enough, right? We haven't done anything great, very complicated, so just make sure you are following. So here the vector tau is of course the wind stress in the x direction and wind stress in the y direction. So if you think about trade winds, those are zonal wind stress and meridional wind stress. Okay, so we will derive the Ekman currents or wind-driven currents as derived by Ekman in one evening. And we will do it in one podcast because he gave us all the solution nicely written up, and we just go through them and see what are the consequences. Okay, so ocean is basically being forced by the winds at the surface, and there is a Ekman velocity being created which forces the interior ocean, and then we look at geostrophy and other large-scale balances in the interior ocean away from the Ekman forcing, Ekman layer.